We continue our discussion of the solutions to the problems from the 26th Philippine Math Olympiad qualifying stage. We are now on part 2, problem number 4. The integers from 1 to 2023 are written on a long blackboard in a straight line. Millie colors any number divisible by 23 in blue, any number divisible by 88 in yellow, any number divisible by both 23 and 88 in green, and any number not divisible by either in red. How many adjacent pairs of numbers have different colors? We start by counting the number of integers less than or equal to 2023 which are divisible by 23 or 88. To do this, let us compute the floor of 2023 divided by 23, the floor of 2023 divided by 88, and then the floor of 2023 divided by 23 times 88. Now, the floor of 2023 divided by 23 is equal to 87, which means that there are 87 integers in blue. And then the floor of 2023 divided by 88 is equal to 22. This implies that there are 22 integers in yellow. And then the floor of 2023 divided by 23 times 88 is equal to the floor of 2023 divided by 2024. The fraction inside is between 0 and 1, so the floor of this fraction must be equal to 0. This implies that there are no integers in green. So all in all, there are 109 integers less than or equal to 2023 which are divisible by 23 or 88. Now let's list down some of these integers. Some of the integers divisible by 23 are 23, 46. I'll just put space in between so that I can insert some other numbers later on. So we have 23, 46, 69, 92, 115, 138, 161. And then some of the numbers divisible by 88 are 88, so it must be here. And then the next one is 176, it must be here, and so on. So the rest of the numbers are in color red. For example, we have here 22, here 24, and so on. Here we have 45, here 47, and so on. Here we have 87, here we have 89. Okay, so what do you notice? So any string of red, blue, red, or red, yellow, red yields two pairs of integers of different colors. For example, in this string of red, blue, red, we have one pair of integers of different colors, and then another pair. Here, we have one pair of integers of different colors, and then this one is another pair of integers of different colors, right? However, we cannot directly conclude here that the answer is 2 times 109 or 218 because It is also possible that an integer in blue is adjacent to an integer in yellow. That is, we can have the string red, blue, yellow, red, or red, yellow, blue, red. In which case, we would have a different number of pairs of integers of different colors. For example, this one is one pair, this one is another pair, and this one is another pair, giving us three pairs of integers of different colors. The same is true with this. This one is one pair, another pair, this one another pair. So how do we determine whether blue and yellow integers adjacent to one another exist? Well, one approach is by guess and check. You just continue the list of integers that we have here. However, that would be a lengthy process. So I would be approaching this differently. So what I'm gonna do next is represent the integers divisible by 23 by 23y, and then represent the integers divisible by 88 by 88x. So let 23y represent the integers divisible by 23, where y are integers from 1 to 87. Similarly, let 88x represent the integers divisible by 88, where x are integers from 1 to 22. Now, if indeed adjacent blue and yellow integers exist, then the difference of the two integers must be 1. So here we consider two cases. First case, 88x is larger than 23y. So we have the Diophantine equation 88x minus 23y equals 1. So this is case 1. Case 2, 23y is larger than 88x. So we have 23y minus 88x equals 1. Let us solve this one separately. You can follow a standard method of solving Diophantine equation or linear Diophantine equation that usually involves using the Euclidean algorithm, but I will not apply that here. My approach here is to solve y in terms of x. So for case 1, we have that 23y is equal to 88x minus 1. And then y is equal to 88x minus 1 divided by 23. Now, I'm going to write 88x as a difference between 92x and 4x. So we have this fraction. Now, 92 is divisible by 23. So we can write this equation as y equals 4x minus 4x plus 1 divided by 23. Now, since we want y to be an integer between Take note, between 1 and 87, it must be that 4x plus 1 over 23 is an integer. So we can check. 4x plus 1 can be 23, 46, 69, 92, and so on. In other words, 4x plus 1 must be a multiple of 23. Now you can easily check that the only number that works here is 69. So if 4x plus 1 is 69, then x is equal to 69 minus 1 over 4, which is equal to 17. Now let's check if 17 falls on the range for the values of x. Indeed, 17 is in this range. So we can now solve for y. So y is 4 times 17 minus 4 times 17 plus 1 divided by 23. Simplifying, we should get y equals 65. Okay, so now we can determine the two adjacent integers. Take note, we have 88x and 23y. So 88x, that's 88 times 17, which is equal to 1496, and then 23y, that's 23 times 65, which is equal to 1495. Alright, so this one is in color blue, this one is in color yellow. Okay, so let's explain this one. So we have the number in color blue 1495 adjacent to the number 1496 in color yellow. So to the left of 1495 is the number 1494 in red, and then the number to the right of 1496 is 1497. So this one gives one pair, this one another pair, this one another pair. Alright. Similarly, we can solve the second case as follows. We can solve for y in terms of x. So we have y is equal to 88x plus 1 over 23. And then I can write this one as 92x minus 4x plus 1 all divided by 23. And so y is equal to 4x minus the fraction 4x minus 1 over 23. Similarly, for y to be an integer, 4x minus 1 divided by 3 must be an integer, which implies that 4x minus 1 must be a multiple of 23. So we have to check also that the possibility that 4x minus 1 can be 23, 46, 69, 92, and so on. But only one number here works, and that is only 23. So let's solve for x. So 4x minus 1 equals 23, gives x equals 23 plus 1 over 4, which is equal to 6. Now we can solve for y. So y is equal to 4 times 6 minus 4 times 6 minus 1 over 23. Simplifying this gives us y equals 23. Now, if x equals 6 and y equals 23, then the numbers we are looking for are 88 times 6, which is equal to 528, and then the other one is 23 times 23, which is equal to 529. Okay, so now this also gives us a string of red, yellow, blue, red. So we have here 527, 528, and then 529, and then 530. So this gives one pair, another pair, another pair. So now we can conclude that there are 105 red, blue, red, or red, yellow, red strings, and that gives us 105 times 2 pairs, which is equal to 210, plus the 6 pairs, this one, plus 6. This gives us a total of 216 pairs of integers of different colors. So the answer is answer choice D. Problem number 5. Let R and S be the roots of the polynomial x squared plus 2x plus 3. The value of 1 over r squared minus 1 plus 1 over s squared minus 1 is blank. Alright, this is just a direct application of the Vieta's formula. Before we solve this problem, let us recall first the Vieta's formula for quadratics. Now, if we have the quadratic equation ax squared plus bx plus c equals 0 with roots r and s, then the sum of roots r plus s is equal to negative b over a, and the product of roots rs is equal to c over a. Following these formulas, we have that the sum of roots of x squared plus 2x plus 3 is r plus s equals negative 2, and the product of roots rs equals 3. Now, our goal here is to express 1 over r squared minus 1 plus 1 over s squared minus 1 into another form that contains r plus s and rs, so that we can use the values negative 2 and positive 3. Okay, so we have the given 1 over r squared minus 1 plus 1 over s squared minus 1. Let's get the LCD to combine the fractions. So the LCD is r squared minus 1 times s squared minus 1. The numerator is s squared minus 1 plus r squared minus 1. Combining, we have r squared plus s squared minus 2 divided by, if you multiply the denominator, we should get rs squared minus r squared minus s squared plus 1. So now, how can we express the components of this expression into an equivalent form that contains r plus s and rs. Recall that we have the identity a plus b squared equals a squared plus 2ab plus b squared, right? So how can we come up with something like this? Now, I can write the numerator as r squared plus 2rs plus s squared. So this part here can be written as r plus s squared, just like this one. Okay, but take note, we are not changing the value of the expression, so we should subtract 2rs and then minus 2. So take note, 2rs and minus 2rs cancel, so you just get the same expression above. Now, how about the denominator? How can we come up with something like r plus s squared? So what I'm gonna do is write the denominator as rs squared minus quantity r squared plus 2rs plus s squared minus 2rs, and then outside this group is a term positive 1. So we are applying the same process in the denominator. Take note again, we are not changing the value of the expression. So 2rs minus 2rs, that's just 0. Now, look at this and this one. You can write that as r plus s squared and then minus 2rs minus 2, all divided by rs squared minus r plus s squared minus 2rs plus 1. Now, we can use the values negative 2 and 3. So r plus s is negative 2, rs is 3. So let's replace r plus s by negative 2. So we have negative 2 squared minus 2. rs is 3. So this is 3 squared minus r plus s is negative 2. So we have negative 2 squared minus 2 times 3 plus 1. Now let's simplify this to find the desired value. So we have 4 minus 6 minus 2, all divided by 9. So the number inside is just 4 minus 6, and that is negative 2. So this one is equal to 4 minus 8 over 12. So 4 minus 8, that's negative 4. So we have negative 4 over 12. And finally, the answer we're looking for is negative 1/3. And that is answer choice B. Problem number 6. 8 people are to sit around a round table on equally spaced seats. 2 of the 8 people, Alice and Bob, insist on sitting next to each other. Meanwhile, another 2, Clara and Don, insist on sitting opposite each other. How many ways are there to seat the 8 people? Rotations are considered equivalent. Alright, let us start by creating a diagram. So we have a round table around this table are 8 equally spaced seats. Alright, now I can place Clara in this seat and then done here. Now let us count the number of ways we can seat Alice and Bob such that they are next to each other. One way is that we can place here Alice, here Bob. And take note, we have 4 remaining vacant seats. And so we also have 4 remaining persons to arrange, right? We can arrange these 4 remaining persons in 4 factorial ways. That is, I have 4 options for this seat, 3 options here, 2 options here, and 1 option for the remaining vacant seat. That's 4 factorial ways of arranging the 4 remaining persons. However, another possibility is that I can put here Bob, here Alice. And then I can do the same thing with the 4 remaining persons. I can arrange them in 4 factorial ways. Right? Another way is that, or another possibility is that, I can put Alice here and then Bob here. And again, we have 4 remaining vacant seats, and I can just arrange the 4 remaining persons there in 4 factorial ways. However, I can also reverse the positions of Alice and Bob. That is, I can put here Bob, Alice here. And then I can arrange the 4 remaining persons in 4 factorial ways. Right? So, in this side, we have 4 possibilities for the positions or seats of Alice and Bob. Now, if we seat Alice and Bob in this side, we also have here 4 possibilities. All in all, there are 8 possibilities for Alice and Bob, right? But for each of these possibilities, we can arrange the 4 remaining persons in 4 factorial ways. So, the total number of ways we can seat the 8 people around this table is just 8 times 4 factorial. So, we have 8 times 24, and this is equal to 192. So the answer is answer choice C.